Hi, and welcome to Week 9, Correlation and Regression Analysis. This video we're going to cover the introduction to correlation and regression analysis, and you can see there that there are the textbook references listed, and this is part 1 of correlation and regression analysis. So the learning objectives are there for you just to focus on the fact that we're essentially looking for the objective of being able to use regression analysis to help us with decision making in business. And in that sense also we'll be looking to use a regression model for prediction. Some of the types of relationships that we can expect to find. Some examples: how do wages of employees depend on years of experience, years of education and gender? How does the current price of a stock depend on its own past value as well as the current and past values of the market index? Another example where we'll be looking for relationships through regression analysis. So it's a study of relationships between variables. It uses past and current data to model the relationship across those variables, and then once you've got that model, we can use it to predict into future time periods. Very, very useful tool in business, used across all business sectors, because many of the market situations involve looking at variables that can help to explain an outcome. We need to get a few fundamentals in place in order to understand this, so let's focus on the types of variables that are involved in correlation and regression analysis. Firstly, we have the dependent variable labelled Y. It's also called the response variable. It's actually given lots of different names that simply can't be restricted to one, so it's a matter of just becoming used to those. It is quantitative in nature, so we will be looking at regression analysis only where the dependent variable is quantitative in nature. You can have regression analyses that deal with qualitative dependent variables, but that's beyond the scope of this course. So our dependent variable, the Y, is quantitative. The independent variable, or the explanatory variables, also referred to as the predictor variables, will be labelled X1, X2, X3, depending on how many there are. In regression analysis, we'll be dealing with simple linear regression analysis, which makes it nice and straightforward because there'll only be one explanatory variable or one independent variable, same thing. Now, the independent variables can actually be quantitative or qualitative in nature in the regression model that we cover. So for example, if we're looking at the relationship between wages of employees and how that depends on years of experience, years of education and gender, from that example, wages would be the dependent variable Y, okay, denoted by the letter Y, so that's what we're looking to predict. And the independent or the explanatory variables in this example are years of experience, years of education and gender. Now, given that we've already covered data types, it should be nice and easy for you to determine that years of experience as an explanatory variable is quantitative, years of education also quantitative, but gender there is an example of a qualitative independent variable. We also need to understand that there are both deterministic and probabilistic relationships. A deterministic relationship is where a value of the Y variable can be precisely predicted from a value of the X variable. So an example of that is price of a house and the sales tax payable. So sales tax is a percentage of the price that you pay for a home. So once you've paid the price of the home, the amount of sales tax payable is completely determined, as opposed to a probabilistic relationship where the value of the Y variable cannot be precisely predicted from a value of the X variable. So for example, if you were looking at price of a house and the size of a house, Okay, so in that instance, the size of the house is what would help to predict the price of the house, but the size of the house does not completely predetermine the price of a house. There are other variables that impact on the price of a house, such as the size, whether or not it's a period home, the location, how old the home is, type of heating, and so on. So in that sense, a probabilistic model comprises a deterministic part and a random part. And it's the random part that accounts for variables that aren't even included in the model. For example, some variables may not even be measurable. In regression analysis, we are concerned with probabilistic relationships only. Okay, in looking at the objectives of regression analysis, we have two broad objectives. The first one is explaining how one or more independent variables combine to determine the response, or the dependent variable. So it's about understanding how the variables combine. For example, in that instance, we're talking about explaining how the variables, years of experience, years of education, and gender combine in any company to determine wages. The second objective of regression analysis is then to use that model that's been determined and defined to predict a value of the response variable from one or more independent explanatory variables. So once the model has been developed that tells you how X and Y are related, that's the first objective. The second objective then is to use that model to be able to predict outcomes of the dependent variable. For example, predicting future sales levels of a company given past advertising and sales levels. Now, we'll begin by looking at how we use a graph to find relationships, to identify relationships between variables. We call those a scatter plot, and you're already familiar with how to produce a scatter plot, so just a brief background on that. A scatter plot is a graphical plot of two quantitative variables that helps to identify any relationship between two variables. We must decide which variable goes where, in other words, on which axis. In regression analysis, the independent variable is what goes on the x-axis or the horizontal axis, same thing. The dependent variable, that is the y variable, is what goes on the vertical axis. So let's have a look at an example. In a company named Datacom, the human resources manager of Datacom Inc. wants to examine the relationship between annual salaries, which is the dependent variable, and the number of years employees have worked at the company, which is our independent variable X. So here we can see that we've used Excel to produce a scatter plot between those two variables. Now, on the left of the screen there, I've included some instructions on how to produce the scatter plot for those of you who need a reminder. Also, in the video that follows this one, the YouTube video, you'll see, actually it's not the one that follows this one, it's the second YouTube video that gives you, again, specific instructions as to how to produce the scatter plot and, importantly, how to edit it so that it's optimal in presenting the information that you're trying to present. But for the moment, let's look at the graph, the scatter plot here on the screen, and we see that years employed, our independent variable, is indeed on the horizontal axis, and on the y-axis we have salary. So what can we see from that scatter plot? That scatter plot indicates that there is actually a positive linear relationship between those two variables, so between number of years employed and salary. Now that's the first part of the statement, that there is a positive linear relationship, but you need to explain what it is about that scatter plot that tells you that the relationship is positive and linear. And so here's the important part, and that is the points tend to rise from bottom left to top right. That is what tells you that this is indicating a positive linear relationship. So that is what you need to be able to explain when describing, in particular, this scatter plot. The relationship, however, is not perfect. The important thing to note about the correlation is that it is positive and its magnitude is strong. So always needing to talk about whether or not it's a positive or negative relationship and whether or not it is a strong, moderate or weak linear relationship. Okay, that was looking at a scatter plot, so that's where you're looking at a visual representation of the relationship between the two variables. We also have a number, a correlation coefficient, that can help us describe the strength of the linear relationship. There are many different correlation coefficients, but in this unit we will only use the Pearson's correlation coefficient. It is a numerical measure of the strength of linear relationship between x and y. Now we need to be careful because the correlation coefficient can be misleading for non-linear relationships. So you still might get a correlation coefficient that is a number between 0 and 1 or -1, but if it is a non-linear relationship, it can be misleading, and the only way, or the best way, that we can avoid that confusion is to make sure we do indeed have a look at a scatter plot first and then look at the correlation coefficient. For a population, the correlation coefficient is denoted by rho, and that indicates that it's the population coefficient between x and y. From the sample, the correlation coefficient is denoted R. So this notation here is telling me that we're looking at the correlation coefficient from the sample between variables x and y. So this is the point at which to get into good habits and be able to record your information using that notation. So the sample correlation coefficient takes on a value between -1 and +1. And this is the formula that we use to calculate the correlation coefficient, but don't have a heart attack, it's okay. You don't need to be able to use this formula. You will use Excel instead, yay Excel, to calculate the correlation coefficient for you. Okay, so for those of you who are interested in formulae, there it is, but you do not need to use that. You instead use Excel to give you your correlation coefficient. So looking at a few examples. Points are scattered about a line whose slope is either positive or negative in correlation. If your, and here we are now using the notation, if your correlation coefficient is greater than 0, it implies that there is a positive correlation, that is, a positive slope. Okay, so there's an example where we have points increasing and moving to the right, so moving from the bottom left to the top right, indicating a positive linear relationship, and indeed the points are fairly close together, so we would expect the strength of that relationship to be high, and indeed it is high as it's close to 0.95. Now I should say at this point the correlation coefficient ranges between -1 and +1. -1 indicates a negative linear relationship. +1 indicates a positive, perfect linear relationship. 0 is where there is no linear relationship. Okay, so correlation coefficient less than 0 implies negative correlation, that is a negative slope. So we can see here that the points move from the bottom right up to the top left. That indicates that it's a negative linear relationship. In this case, correlation coefficient of -0.86. Now another point to consider at this point is a negative relationship is not worse than a positive relationship. It's all about the magnitude of the correlation coefficient. So for example, if I were to ask you which indicates a stronger linear relationship, a correlation coefficient of -0.9 or +0.8. Okay. The answer there is -0.9 is a stronger linear relationship. It just happens to be negative. It's an inverse relationship. It just means that as x goes up, y goes down. But it is stronger than positive 0.8 because the number is lower. So we need to get used to that. Okay, perfect correlation is when all points are in a perfect straight line with the slope being either positive or negative. R equaling positive 1 implies a perfect positive correlation. Okay, as you can see there. R equaling negative 1 implies a perfect negative correlation. Now, I have to say at this point that if I produced a scatter plot on data that looked like that, I'd be very worried. That never happens in reality, and if something looked like that, I would think that there's a mistake somewhere. In fact, if something looks like that, you're actually dealing with a deterministic relationship, right? Because x is completely determining y. So not really what you want to see. And there we go. That's the point that I've made there on the slide. Okay, zero correlation is where your correlation coefficient is approximately 0 with 0 slope. The points are scattered about a line whose slope is 0. So there's an example of a correlation between two variables that is approximately 0. So yes, you have a correlation coefficient of 0.03, but in practical terms that's telling you that there is not a linear relationship between those two variables. Now here's an important point to remember. It may be that your relationship is indeed a very strong one, but it is non-linear. So in this example we have a quadratic relationship. Now the correlation coefficient, the Pearson's correlation coefficient, is measuring the strength of a linear relationship. So whilst the second chart here shows a very strong quadratic relationship, it is not a linear relationship, and so our correlation coefficient reflects that. So in that sense we need to be careful that a correlation coefficient is not telling you that there's no relationship at all between the variables, just that there's no linear relationship. And that's why looking at a scatter plot is always important for you to get some sense as to exactly what's going on between those variables. Okay, some examples here for you to have a quick go at. If I asked you, well, think about this now, just say out loud to yourself, I can't hear you, what you think the correlation coefficient would be on that scatter plot. So is it positive? Is it negative? Is it perfect? Moderate? Weak? Hopefully you've said all the right things. So for that one we have a correlation coefficient that would be 1, perfect positive correlation. Okay, what about that one? Okay, so it's not perfect. Is it positive or negative? Heading in the same direction as the previous one, so it's positive, but just not perfect. So it's going to be some number between 0 and positive 1. So I would probably put that as maybe 0.75, 0.8, somewhere around there. Okay, what about this one? Okay, much harder to tell. Is it positive or is it negative? It looks as though x is not really influencing y that much. I would probably say that this is going to come up with a correlation coefficient that indicates no linear relationship there. This one, definitely a linear relationship, but what's special about this? Points are moving from the bottom right to the top left, which indicates a negative linear relationship. Certainly not perfect, but pretty strong. Again, I'd probably give that maybe 0.75 to 0.8. And here we have the opposite of what we started with. Okay, so perfect linear relationship, but negative. Okay, so really it's a matter of practice and experience in looking at scatter plots and being able to make the call, but this is the first piece of information, if you like, that you can use in setting up a regression model. This is convergent validity right here. So this is where you get a sense as to whether or not the relationship is positive or negative, whether or not it's strong or weak. And then when you move to the next step in regression analysis, that is producing a model, you need to check to see that it is consistent with the information you found through your scatter plots. Convergent validity. A note on correlation before we wrap up. When considering correlation, the first step is always to draw a scatter plot. Okay, that's pretty much what I've just said, I think. You really do need to get a sense as to what's going on and to ensure that the correlation coefficient and the subsequent regression model all support or converge to validate the original findings in your scatter plot. Another note, a point to note, since R is a measure of the strength of the linear relationship between X and Y, it's not useful in reflecting the strength of non-linear relationships, which is the point we made earlier when we looked at the scatter plot for a quadratic relationship. Lastly, this is correlation, not causation, a very important point to be clear on. So unless the data is obtained in a carefully controlled experiment, which is not the case here, we can never make definitive statements about causation in regression analysis. The reason for this is that we can almost never rule out the possibility that some other variable is causing the variation in both of the observed variables. So for example, this is an example based on the data that's been collected on all fires in Melbourne for the last 10 years. This is an example that I've used for a long time now, and every time I have to say my brother is a fireman, and when he first saw that I used this example, he asked me to remove it. He wasn't very happy at all, and you'll see why in a second. But it's a good example, so it stays. So this is an example where we've obtained data on all the fires in Melbourne for the last 10 years. And it was found that the number of firefighters at a fire correlates highly with the corresponding damage in dollars. So does that mean that we can conclude that firefighters cause the damage? My brother definitely says no. And of course that is true. We can't conclude that. It's just a good example where both variables result from and are correlated with the overall size of the fire. So it is very important to understand that it's correlation, not causation. Okay, that's all for now. That finishes our introduction to correlation and regression analysis.